Hi everyone, I'm Jared Buckley. I'm a PhD student at the University of Massachusetts, Dartmouth. My advisor is Amit. What I'm going to talk about today is a little study I did where I'm investigating the impact of adding advection into a 1D model, asking whether or not that has a significant effect on surface parameters like SST and SSS. The first thing I want to say is the motivation behind this is if you run a 1D model properly, as there was issue yesterday, what you see is that the SST in the model is too warm for this particular time period at this particular location. So this is from the Woods Hole mooring at 18 North during the year 2015. I initialized it with a profile in that area, and I ran it with the air-sea fluxes that were actually calculated from observations there at that point. And what you see is that it's very, very warm. This purple line up here is PWP, and the blue line is the actual observed SST from the mooring. The difference is, 4 degrees Celsius by the end of the year? It's a big difference. So it's obviously not enough to just have the air-sea fluxes. The obvious question is what's going on? Why is that happening? Could it be advection? Turns out that you can actually ask with satellite data what the near surface currents are, and you can ask what the gradients are, so then you can get some kind of estimation for what the advection would be. And so I made this product, which I called BoBcat, and published in a paper with Sri Lanka from IISC. And it just uses satellite altimeter and some wind and a scaling to try to compress the Ekman depth in the presence of strong stratification like you see in the bay frequently. And using that and other satellite gradients, I got what I think the advection should be. And what you can see here is this is what I calculated to be the advective freshwater flux. It's in meters per second. It's kind of like what you would put into a model as far as rainfall and evaporation is concerned. There's lots of heterogeneity in the bay, but you see these really intense fresh areas, mostly along the edge, less intense towards the center, and areas near energetic currents have higher values. This is the area where the Woods Hole mooring was located. I have a little box here because that's where I'm going to do the study. In there. Oh, this is an average over the study period, which is between February and December. This is the heat flux to show you also. So it's typically between -20 and 20 watts per meter second. Across the entire bay. Again, it has this funny heterogeneity, almost like an eddy field when you average it. The issue with what I'm doing is because satellites are limited in resolution and there's all sorts of approximations going into here, I have a box that's 1 by 1 degree that has a lot of noise in it. So the estimations in here have a lot of variability. I'm not sure how to average that out. So what I do instead is I create an ensemble of all of the estimates that's inside of that box. And then I use that to force PWP. And these are just the equations I use to calculate the advection. The most notable thing is I have the Ekman depth, which I estimated with BoBcat, and I assume that it all linearly decays within the Ekman depth. Here's what the freshwater flux looks like at the Woods Hole mooring location. All these gray lines are the individual points, so there's 25 of them. The orange line is the mean of them, the ensemble mean. This blue here is the actual observed precipitation by the mooring itself. What you can see is that frequently the advective flux is large, often on the order of these precipitation spikes. The spread between all of these members of the ensemble is also very large, both in time and in space. But they frequently show jumps and up and down in similar locations and time, right? And strikingly, you can see these drops in where it's supposed to get really fresh just like you would expect at this location. And for some reason, the strongest advective flux is actually getting saltier towards the beginning of September. This is just what the heat flux looks like. The observed heat flux is smooth over about 2 weeks, so you don't get those big fluctuations. What you can see is, again, there's a spread amongst the members, and the heat flux from advection is often close to the air sea heat flux after maybe May or June. You throw all of this into the PWP model and you run it. So this is with freshwater and heat advection. You get all these gray lines for the SST, which, you know, when you first look at this, you say, I've learned nothing. Right? This is horrible. What have I done? But it turns out that if you just take the average, it looks pretty good. I almost fell on the floor when I did this. I was shocked. This is what it looks like when you do the same thing with salinity. Now, the issue that is going on here is I'm adding this all as a surface flux, so it doesn't surprise me that PWP would be really overreactive to anything that's happening. So you get these huge swings in sea surface salinity. Again, this spread looks ridiculous, like you've learned nothing. When you average it, it gets a lot closer to the real value, but it still has a really significant fresh bias. Not sure exactly why that's true, if there's some kind of systematic thing happening. But what is clear is that if you compare this curve with the advection to the curve without the advection, you do see drops in the salinity around the appropriate time period. So it has some skill at showing the drop in salinity and some skill at showing the surface layers actually getting shallower. This is what happens when you do a lot of ensembles. So what I wanted to do is show how sensitive is the SST to adding, say, just heat, just salt, or them combined together. So the purple line, again, is the control simulation. It's a little bit better towards the end. It's a lot of it better towards the beginning, but it still has a significant bias. When you add in just salinity advection, you get this yellowish line here, which is significantly better. And then adding in heat on top of that, you get that orange line that I showed earlier, and it's not really bad. The most important thing to say when looking at this is that the original only air-sea flux run has a much bigger error than when you add in some estimate of advection. And just for visual sense, I plotted the members of the both salinity and heat advection on top of this. I'll just summarize real quick. Air-sea fluxes are not enough if you're looking to accurately simulate SST and SSS, at least at this location of the bay during this time period. If you're going to use, like what I did, a satellite advection estimate, there's going to be a lot of noise, and you can compensate for that noise by just running a whole lot of simulations. PWP is cheap, so should go ahead and see what we get, and then take the average, and it works out. The evolution of SST is impacted more by the salinity advection than it is the heat advection. So if you want to get anything right, you want to get the salinity advection right. Okay, thank you.